Okay, welcome back to Triplicate and back to the heresy, and hopefully exciting times. Hopefully we will get our bowed bottle model, which I think was the best name we came up with, actually into the synthesizer, and it'll be doing what we hoped it would do. No promises that it's going to sound any good, but at least we'll have a starting point which we can build on. Now, I have been working hard on the code, well, working some on the code anyway, and I've done quite a lot of tidying up and improving its structure, which I won't bore you with. But one thing I have done is included the ability to record and play back what we're playing here. So this is so for debugging I can record a little bit of whatever and then I can just play it back for debugging without having to turn and actually work the player interface. So I'll quickly show you that. So okay, so if we play something totally pointless like a scale, okay, so now as well as the log file for the audio output, we have a text, just a text file. So the audio output for this one, we'll just play this. Okay, so that's a little descending scale we played, and the text file is just a time in milliseconds and 7 values coming out of the player interface out of the STM32, and this checksum number, not a checksum, just a synchronization number. So if we rename this test scale down, and we go into the program and we redefine the per file name as test scale down, whoops, and recompile it. It should play that without me playing anything, so let's see if that works. Okay, pointing the camera at the screen because this program and Camtasia's screen record don't get on together. So we do this and we get a lengthy compile. Okay, here it comes, and there it is. Look, no hands. Yep, just a useful little thing for debugging. So now let's get on and do what we're here to do and try and get this thing working with our bowed bottle model. Okay, so just took the code out of the test program we did several videos ago when we got the bottle working, dropped it in and it went straight in and worked first time, which was just a little scary. So here we go. Scarborough Fair in a different key, but it's not working entirely correctly, but I can fix that. And the first thing you probably notice is it sounds just like the sine wave. So, not really what we wanted, so let's look into that as well. Okay, so here is the log, the WAV file of what we just played live. Etc. No huge musical merit there, and that sounds a bit flat, a bit boring. We're trying to make something that sounds sort of alive, like an acoustic instrument. So let's look at the spectral view of that. Well, we actually do get quite a decent spectrum, so it's not actually playing out a sine wave. So this is the spectrum of that. Now let's all look at me whistling, which is an acoustic instrument. Right, sounds a bit squeaky because recording a whistle seems to be quite hard. But now let's look at the spectrum of this, and look at all this. This is actually noise. Caused by the fact that you get turbulent when you blow through a small aperture, i.e. my mouth. You get turbulent airflow, and that turbulence translates into noise. So let's try and see if we can get some noise into our blowed bottle model, and make it sound a little more interesting. And also let's look at our bottle, our beer bottle, and see what that sounds. Again, we have some noise. It's played. Okay, so let's look into adding some noise to our bowed bottle model. Okay, well, me whistling and blowing across the bottle, the noise is basically breath noise. So here is me just breathing loudly, if you see what I mean. So this is some pure breath noise. So shall we see what that looks like spectrally? Okay, so we can see we have a big chunk at about 1,000 and a bit more here. If we look there and look at the frequency analysis, basically we have a peak at about 1,000 Hertz and then it drops off. So shall we see if we can generate some noise like that? Okay, well, conveniently Cool Edit will generate some noise for us. So let us do just that, noise. Okay, so we want white, pink and brown are low pass filtered, which we want wide bandwidth. So shall we see what that does? Oh, yes. Let's get the waveform view. So there we have some noise. Let me look at that. Right, and I'm sure Cool Edit does the same as every other digital noise generator I've ever come across, and it's just a 16-bit random number generator. So let's hear what this sounds like. A badly tuned radio. Yeah, and got a quick view of it. That is the spectrum, just a ton of stuff everywhere. Now our breath one, so we had a peak at about 1,000 and then dropping off fairly sharply above and below that. So should we add some filtering to this and see what happens? So we can FFT filter. Okay, so here we have a filter, starts at about 500 Hertz and then is maximum of between about 900 and 1200 Hertz, and then falls off, well, it's logarithmically ish. So shall we see what that does? Okay, let's compare that with our breath one. So I think it should drop off a bit steeper. I think that's, before we actually listen to it, we'll do that. So we'll go there. We'll go like that. Should we see what that does? Okay. So what does that sound like? Sounds better, but I'm still not convinced. Right, the normal way of generating white noise is simply to generate a series of pseudo-random numbers. Now, a series of pseudo-random numbers will generate every number in a random order and then go back and start again. So if we're using 16 bits, we've got 65,000 and a 44,000 sample rate, so it goes round every second and a bit, and you can hear it cycling every second. So we want a 32-bit number, which is every whatever, lots of hours, which is fine, but the standard rand function only generates, I think, between 0 and 32,000, so that's no good. However, I am using it to seed my noise 32 number, and the way to generate a pseudo random sequence is to take your last value, multiply it by something and add something to it. And those numbers are just, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3. I just type them in and they seem to work, and I just check the min and max to check it's doing what it's supposed to do. Okay, so noise is a floating point number, just the 32-bit number over 2 billion should give -1 to +1, and then we multiply that by 10,000 to give a 16-bit output sample. So shall we see how that does? Run. And I've got it to save the minimum and maximum of its 32-bit number, which is minus 2 billion odd to plus 2 billion odd, so that's what we want. So let's get rid of that. Let's load this into here. Noise test filter.pcm mono 4014, doesn't really matter. Oh, and that's the spectral view. Not what we want, but well, it's looks like noise. Let's play it. Let's play it. Yep, that's white noise. Sounds horrendous. There you go. Just have a little look at the waveform view. There we go, and if we zoom in far enough, yeah, we see noise. Right. Okay, so we don't want to use our horrible sounding white noise, we want to filter it. We want it to peak at about 1 kilohertz and then fall off either side. So I thought we'd just try for first approximation our good old state variable filter of the type we used in the mean green. So if you look through the synthesis tutorials, I go through how it works in some detail. That's how it works. So it's quite simple, and we just take it produces a low pass, a high pass and a band pass, and we put the noise into the first. We use 2 filters, one after the other, put the noise in and then put the band pass in out of the first filter into the second filter, and take the band pass of the second filter. That's our output, and that should produce 12 dB per octave ish. So let's see how that does. Run. Pretty quick. It doesn't print out a lot of anything interesting. So let's see what that does. There we go. Let's play it. It still sounds a bit flat somehow, but we're gonna try it. Let's look at the spectral view. So that looks about right. We're getting about 1 kilohertz. Zoom in on the frequency. So it's peaking at about 1 kilohertz and dropping off either side. Actually, if we pull the frequency analysis in, we can see in better detail just below 1 kilohertz. Anyway, we are now going to try that in our heresy and see if we can somehow add that and see if it makes it sound less, well, like a synthesizer. So that's the next job. Okay, so let's remind ourselves of how we are working here, how our bowed bottle model works. We're actually using a resonator for our resonator, our simple mass on a spring model. And we've got some damping which I haven't drawn in, so we don't need it for now. And we are imagining, we're not trying to actually build any model of any physical system. This is just a way of getting our heads around what's going on. So there's our bow, which is travelling, say, up, and our mass is going up and down, and our bow is catching on this, I don't know, whatever. And what we have for the force on the mass is this kind of thing. And this is the delta V, which is the difference in speed between the mass and the bow. The bow is going on constantly and the mass is bouncing up and down. And when they're very close in speed, the bow is applying a force to the mass, so giving it a kick, and then when the speed is different, stupid dog, when the speed is different, the bow is having very little effect on the mass. So as a first hit, we want to apply our noise to this force. So what I've done as a first hit, the first approximation, is very simply delta V F noise, drawn a straight line through the origin. Terrible straight line. So the faster the bow is moving relative to the mass, the more noise is in, which seems pretty reasonable. So let's see how that performs. Okay, so here we have the advantage of being able to play a pre-recorded performance. So we can try exactly the same performance with several versions of the code. So this is the original with none of our bow noise added, and I've just taken a little section, and if we look at the spectral view, zoom in a bit, yeah, we get a few nice harmonics and nothing in between us. So we are trying to remember this noise related to the pitch sound, but throughout the spectrum. So now let's add, well, it's an arbitrary scale of the amount of noise we're putting in, but it's 10. This is 10. Okay, and you can see we do actually have some of our noise appearing in the spectrum. So how does that sound? You can hear the noise coming in, but it's not a particularly good sound to it. I'm trying to get that sort of smooth sound that you might get with a violin, a bowed violin. Yeah, so okay, let us try twice as much. We've got an amount of 20 and a bit more noise. Again, let's see what that one sounds like. Sounding more scratchy and crackly than sort of smooth the way we want it. So it doesn't look like this is doing what we want it to do. So finally, let's try a noise scale of 50. Yeah, lots more noise, and there's the play button. Sounds like somewhere there's a really bad electrical connection. So our first attempt at adding some noise to our signal, we can't really claim to be a success. However, onward and upward. I shall have to have a think about what's going wrong there and how to put it right. Well, I think I'm going to end it there, because these videos seem to take quite a long time to make, because I'm having to make everything up as I go, and it's probably going to take me a little while and head scratching and trying stuff out to figure out why this noise idea isn't sounding very good. I still stand by the idea I'm sure every real instrument, blown or bowed, has some noise element in the sound which makes it sound richer and fuller than just, you know, the pure spectrum you get out of a synthesizer. So I'm going to press on with it, and the next video will probably be about me hopefully solving the problems. So for now it's goodbye from the heresy, and it's goodbye from Triplicate. See you soon. Goodbye.